let us start anew. Okay, good morning once again. Apologies for the technical difficulties. Let me start again. So today we are going to talk about classes, objects, and polymorphism, so object-oriented programming in short. So I mentioned this before in the procedural programming session. We are slowly moving away from the basic building blocks of a programming language that you have seen with C and C++. Things like types, how to allocate memory, how to do branches, how to do loops, things like that, which in principle you have probably been told is some high-level human readable abstraction, so something we can read and write, which we then pass on to a compiler who will know the rules, how to translate that into machine code. So finally, giving us something that the machine can run. Now, the terms procedural programming or object-oriented programming have very little to do with actually translating human-readable code into machine code. Instead, these are programming paradigms and approaches how to tackle problems. So there is very little, or there's pretty much nothing you cannot achieve with procedural programming, which you can with object-oriented programming and vice versa. So you can make all the functionalities you want either way, but you don't necessarily want to. Certain problems are more naturally suitable for procedural programming, others for object-oriented programming, and this entire exercise, this entire concept is here to make your life easier and to make your programs sustainable, maintainable, and workable. So, to emphasize that, I'll give you another quote from Edgar Dijkstra, that the major cause of the so-called software crisis is that the machine have become way too powerful, several orders of magnitude more powerful. To put it quite bluntly, as long as there were no machine, programming was no problem at all. When we had a few weak computers, programming became a mild problem, and now we have gigantic computers, and programming has become an equally gigantic problem. So once you start working on and developing your own code, which is several hundred thousands of lines of code, you need a way to make it manageable, you need a way to make it readable, understandable, testable, developable, workable. And this is where part of the motivation for object-oriented programming, or OOP, comes in. So it allows you, for example, to model systems more naturally by describing objects based on their attributes and their actions, and by describing relation between those objects. So certain problems, imagine for example you're like me and you're writing numerical simulations which include particles. Having particles designed as a type of object which can interact with each other is a very helpful way of designing and writing a program for particle simulations. Now, OOP is also helping to improve maintainability by enforcing encapsulation. So you encapsulate code, we'll talk about this more in detail later, via member access control, while also enhancing code reusability using composition and inheritance, which are two concepts we're also going to go through today. So just as a quick aside, the differentiation between object-based programming and object-oriented programming, well, in an object-based program, or in object-based programming, we want to write programs in terms of objects and operations acting on this object. So, in contrast to object-oriented languages, object-based languages do not support polymorphism, which is also something we're going to talk about in a moment. So essentially, you will have objects and you will have things acting on those objects. However, in object-oriented programming, It's a programming style, a paradigm, that focuses on the design, the implementation, and the use of class hierarchies. And that's classes are also something we're going to look into quite a bit of detail starting now. So, what is a class? By definition, a class is a type. Same as you have those native types, such as integers, floats and doubles, characters, things like that. A class is also a type, and the class definition, which you write, introduces a new type. Now, an object, on the other hand, is just some memory that holds a value of some type, right? And C++ programs create, destroy, refer to, access, and manipulate these objects. The object will occupy some region of storage, so some memory, in its period of construction, while it's alive, so throughout its lifetime, and while it's being destructed. Now, in C++, the object must have a size, some storage duration, a lifetime, a type, a value, and optionally it can have a name. Now, I really should emphasize here, today's session on object-oriented programming is exclusively on C++. C does not permit you to write classes, so this is a C++ feature only. Okay, now, let's say the goal is to show you how you can write a class. So let's dive into that. Now, what is a class composed of? Well, a class is basically a custom data type which consists of member variables and member methods. And the idea behind it is that it encapsulates both state and behavior of something. So the state is stored within the variables, and the behavior is stored with the member methods, or member functions, if you will. Now, and each object will have a copy of each member variable, but not necessarily the same value, right? So you can think of it, every car will have a color, but the color will not always be the same. Yeah? If the car is the object and the color it's the variable we are storing, every one of these will have the property, but the property is not necessarily the same. You can change what it is. Similarly, for member functions, the idea behind the encapsulation is that they can only be called on objects of their corresponding class type. So if I have a member method, let's say drive for a car, if I have a member method, I can only apply it to the object of type car. I cannot apply the same method to an object of type bicycle, right? And in principle, you can see member functions as pointers that are valid class-wide. So they are somewhere in memory, and every object knows where in memory that's going to be and goes and fetches this memory, what the contents of the function are. Okay, so let's look more closely at quite default class specification in C++. So we started by declaring this is going to be a class, and we're going to give it a name. By convention, the name is going to be starting with uppercase and in camel case, and then you have the curly brackets, and then we have what we call access specifiers, this public and private. We'll talk about that in a second. Then we have this strange looking thing here, which also is called class name and takes some parameters. And then we can define more methods. So method 1, method 2, method 3, which has some return type. They can naturally be very different return types. So method 1 could, for example, return an integer. Method 2 could return a float. Method 3 could return a double, etc., etc. And they can all take whatever parameters you like. So those here in the public section are member methods. Here below, in the private part, we have what we call member variables. So you see they have a type and a name, as usual, declared. Now, let's look more closely into this, what we call access specifier, this public here and this private here. So the access specifiers, they specify access rules for members, so both functions and variables, and they follow it until the end of the class or until another specifier is encountered. So if you look at here, all of we say public, so all of this remains public until we introduce private, and then until the end of the class is going to be private unless you write public again, and then it's going to be public until end of the class or something else shows up. Now, public means that a member, so public member, can be named anywhere without access restrictions. And here we are coming into this encapsulation bit. So what does that mean in practice is that if you declare a member variable or a member function as public, it means that anything can call access either the variable or the member function anywhere in your code, right? So whereas private means they can only be named by members and what we're calling friends of the class. We'll get into that in a minute. So only essentially in the class itself where it is declared. So let me elaborate a bit more on that. The idea here is, once again, encapsulation. And this has, once again, nothing to do with what a compiler can and cannot translate into machine code. The idea here is to impose rules on yourself as a developer and on others who are developing. So the idea is to say, look, these functions and these variables you are supposed to look at. You're supposed to use, right? Like, get me some value or tell me something about yourself. These are going to be public, and this is what you can call from outside of the class. Whereas you want some internal machinations, some internal computations, anything internal which is not supposed to be public-facing, essentially you're telling other developers and yourself, you're not supposed to look at this or touch this at any point while outside of this class itself. So outside of the declaration on definition of the class. So anytime you're specifying or defining a function, a member method, you can use all private variables in there, while specifying the member function of this specific class. You cannot then access it from outside of the class, unless you specify it as a friend. So you need to specifically do this. Otherwise, by the rules of the language, the compiler would say, you're doing something prohibited, you're not allowed to touch this. And the entire idea behind this is, again, encapsulation. Basically tell the program how you are intending on using it and how you intend on writing it. What should you be able to touch from the outside, and what should you be prohibited and should never have to look at from the outside. So this may not make too much sense to you right now, but again, once you start writing, what you could do, for example, is write an entire external library which has a single object as its interface, right? So, for example, let's say you write an entire library which is something that creates the window which you're looking at your screen. So every time you open a program, it will open in a window. And in this case, what the library could, for example, do is provide you, every time you get a single object out of it, which is make a new window. And then you will have access. You will have members such as add a new button, add a second button, add a third button, and each one of these buttons is going to do something. But you do not want anybody from outside to be able to modify what a button is and how it works, unless you specify exactly how to do it. So you can basically specify an API with that. That's the whole idea of the concept. Now, let's look at a more concrete example. Say we want to define a new type of variable or a new type of object which is supposed to store a complex number, a concept I'm sure all of you have heard before, but it's not a native type in C++, so let's develop our own. So we're going to call it complex number, and this first thing here is called a constructor. We'll look into that in a minute, but it has the same name as the class by definition. So this is what makes it a constructor, and it takes as many arguments as you like. This thing is called an initializer list. I'll come back to that in a second. And our complex number type, let's say, should have a method which returns the absolute value. So we'll fill that out later. And it should also give us the conjugate as a type of double. This is another public method. So these have to be public because this is something I want to use on the object. So I want my user or myself to be able to use these methods, right? Whereas the internal storage, anybody else is not supposed to actually touch, at least for now. So we declare those variables private, which with a real part and an imaginary part, and we're adding another underscore there so we don't get name clashes with, for example, these arguments we're here. And now you will see here we have what we call this initializer list, and here this real, which we have down here, comes up again, same as imag, so the imaginary bit. These are the variables that we're storing. And this is essentially instantiate or initialize the object by its default initializer, because all the native types, integers, floats, doubles, etc., are also objects. So this is a basic instantiation, basic initialization of our private members, right? So how do we instantiate it? We can go, we use it as a type. So if we were using integers with doubles, this would be integer A. Instead, we have complex number here now. We give it a name, which is A, and some initial values. Here, for example, 1 and 2. And then, if we wanted to call this the apps method, you would just call it with a dot apps. So, an alternative way, since C++11, called uniform initialization, is you can also use the curly brackets here. That, curly brackets here. That also works. Now, you may recall that C, for example, and C++ as well, also have structs. So what's the difference in C++? Again, because this is only valid for C++, what's the difference between a struct and a class? Well, essentially, they're the same. We use both to create custom types, and both can have member variables and member functions. But the difference is their default behavior. The default accessibility in struct is public, so if you don't write any access specifier, it's going to be public in structs, and it's going to be private in classes. Now, by convention, we use structs typically to aggregate data, and only data, while we use classes to bundle data and associated operations. So a struct you will typically have structs when there's no member methods assigned. But again, this is just convention. Nothing prevents you from adding it if it helps. Yeah, and just as a side note, the C++ standard, so if you're reading that to read up on the rules of how things work, they uses the term class type as a superordinate for structs, units, and classes sometimes. So if you see something like a class type can do this and this, it means structs, units, and classes. Okay, now let's look into member functions. We have seen a couple of those, like the absolute value or the complex conjugate. But there are a couple special ones, and we already seen one of them, which we call the constructor. Now, the special member functions are here to ensure that these custom types, that we can use these custom types just same as the built-in types, like the integer and floats and doubles, and they are required for resource management. And let's start with the one we've already seen, the constructor. It's a special member function of a class, which is used to initialize objects of the class. So it does not get a special name, so you don't name it differently. Instead, it has the same name as the class type. And whenever you initialize an object, it will be invoked, it will be called. And it can only be called once in a lifetime of an object. Now, you can call them without any arguments. And you can use so-called, default constructors, which will be compiler generated. So the compiler, even if you take no arguments, the compiler will have to do some things like allocate memory for all the member variables, etc. So that the compiler will do for you, unless you want to do some special things with it, where you add more arguments and do stuff, whatever you need. And there's also a second type, a special type of constructors we call copy constructors, which is where you take another object of the same type of the class as an argument, with the idea I'm going to copy the contents of the other object into my object during initialization. So I want to create a copy, initialize or construct an object as a copy of another one. That's why it's called a copy constructor. Similarly, we have move constructors, where instead of creating a copy, we are taking over the resources. So we are moving them, leaving whatever was in the other objects we are taking things from in an invalid state. So it's basically empty, which can be very, very useful if you have objects which take up a huge amount of memory. So if you have an object which stores a massive array which takes almost your entire memory, you would rather want it to be moved, so just assigned all the data assigned to a different operator, rather than making a copy, which will make your code crash because you run out of memory. So those are some of the use cases for resource management. And we'll see the syntax in a bit. So let's look again at in more detail at the constructor definition. So again, we have a class which we'll call X. The constructor, of course, needs to be public because that needs to be accessible from everywhere. It needs to have the same name as the class, so in this case X. It can take any parameters you want. And this is again called initializer list. So you're essentially, and now you can see here, this is a copy initialization using a copy constructor of, so we have a private variable A underscore and B underscore. Here's an A underscore initialized as a copy of integer A, and B underscore initialized as a copy of B. Right? So it may be important to remember and to know that the member variables are initialized in the order of their declaration, meaning not in the order in which they occur in the member initializer list. So if B and A were swapped around here, A is still going to be initialized before B. And yeah, for, I believe, quite obvious reasons, it should be good practice that the member initializer list, so this bit here, should have the same order as the declarations to avoid any confusion and problems. However, if you would like to specifically assign values to your member variables, you can do that as well. You don't have to use an initializer list. So you can specify, so here's the function body or the method body for the constructor. And here we can explicitly assign the values. Typically, you do that when you need to do some special operations. For example, if in this case we are having an array and we want to allocate some memory for it dynamically at runtime, then you can't do that in initializer list. So that is something that you will typically do with a constructor. You do that inside the function body. Now, it's good practice to prefer member initializer lists over initialization via assignment, which we're doing here for performance. So what we could have done here is take the size argument into the initializer list and keep the memory allocation in the function body. Okay, now we mentioned this one before, the so-called copy constructor, which initializes an object from another object of the same type during initialization. So for example, if we have some type T, the use case would be A of B, meaning initialize. So this would be a declaration of and definition of the object of type T. A, make it a copy of B, or type A equals B. They're basically the same, but of course B must be of the same type as A for it to work. Yeah. So it also comes up when we're returning values, because you always return a copy. So you return a type of a type F, or when we're passing something into a function. So you always get a copy of whatever you're passing. So as a function argument. So if we have a function which takes an argument of type T, so here a function which takes an argument of type T, if we pass it in there, the copy constructor to make a copy of that object will be called, right? And what's the correct syntax for it? Well, this is our usual constructor, which has for our class complex number, which has the same name as the class, and then takes any argument we want. And this is the so-called copy constructor. It must take a reference of the, so yeah, this should be complex number here, apologies for the typo. So it must take a reference of the same class. How you name the reference doesn't matter. So it doesn't need to be named other, but this should be complex number. It needs to take a reference of the same type, and the function method name must be the same as the class name, and this is what defines the copy constructor. So, and once again, we've been talking about these public and private accessors before, and you may remember that image underscore and real underscore used to be private variables, but here we are using them within. We're using the others, imaginary and real bits. So why does that work? Again, these private and public declarations are not on an object based, they're based on the entire class. So anytime you're working on the class specification, if you're writing your function inside the class, you have access to everything all the time. Right? So we are still inside the class specification. It works on per class basis, not a per object basis. Okay. Now, we had a constructor when the object is initialized. Similarly, when an object is destroyed, when its lifetime is over, for example, at the end of the program, or at the end of a block or a function, for example, you instantiate an object just like normally allocated on a stack, And once you reach the end of the block, the memory gets freed again, like all other data types. And this happens for objects for which you write the type, so for the classes you're writing as well. And this happens with structure member function. Now, it's a special member function that is called when the lifetime of the object ends, and its purpose is essentially to do everything that needs done by the end of it. Most importantly, if you, for example, at any point in the object's lifetime, allocate some resources manually, so you allocate memory on the heap using malloc or new, if you don't remove it correctly, you will have a memory leak, which can very quickly become a massive problem. So this is what we have destructors for. So any resources that the object may have acquired during the last time they are freed in here. And by definition, member variables are destructed in reverse order of their declaration. And essentially, you need it whenever your class manages resources with some dynamic storage duration. So again, if you're using something like a new or a malloc. There are a couple of very, very fun tricks to be used with destructors, because anytime you instantiate an object, you can instantiate it on a stack. Anytime a function ends, for example, the destructor gets called, which means that you can use this to your advantage. For example, if you want to print out, I'm finished with this function, you can put that in the destructor, and whenever the function finishes, it will automatically, while calling the destructor on the object, print something out. So you can use it, for example, to time your functions or do whatever else you like. So there's a couple of nifty tricks with them around. Okay, so how do we define the destructor? Well, here again, we had for our non-specific class called X, this was our constructor with some method body. So it had again the same name, takes however many parameters you want, including none. And this bit here is the destructor. So it has a tilde and again the class name, and takes no arguments. And this, then you do in here whatever you need done. That's your destructor. So there are a couple of others. So here's a more or less comprehensive list of these special member functions. We don't have time to go through all of them in detail, but it might be good for you to have an oversight of what's around. So we've seen the constructor, which initializes an object. There is a destructor, which frees the resources the object may have acquired, and it's called at the end of the object's lifetime. We've seen the copy constructor, which is used to initialize an object from another object of the same type. We've seen a copy assignment operator. No, we haven't seen that. There is a copy assignment operator where we assign a new value from another existing object to an already existing object. There's a move constructor, which I mentioned before, which is similar to the copy constructor, but instead of actually copying the data, it just reuses the resources, which can come in handy if you again have dynamically managed resources. And similar, we have the move assignment operator, where we replace one object with the other object by swapping the resource code. And the good news is you don't have to keep writing those all by hand. You only have to do this if you're doing something special which needs attention. In particular, the most common use case is if you have dynamically managed resources. Other than that, especially for trivial cases, you can just leave them empty. Or default, or not mention them at all. And there's also a great article on what we call the rule of zero. So there's a rule of 0, rule of 3, and rule of 5, which tell you essentially, well, if you need to write one of these special member functions, you are very, very likely need to have to write at least 3 or 5. So I recommend looking at this article. And to sum things up, or to show you the syntax of what the operators should look like, again we have this class X. The constructor, which can take any amount of parameters you like. If you want to use the default one, you can specify equals default. And the compiler will then just generate one for you. You don't have to do anything. The copy constructor needs to take a class of the same type, which is constant and a reference. And you can call it whatever you like, but it needs to take at least one. And again, you can, if you don't want to write it, you can write default. Similar, the copy assignment operator. So we can write operators for our types or for our classes. We'll go into more detail in a minute. So this is the copy assignment operator. This is the syntax for it. This is how you write it. Again, you can use just a default. The move constructor takes a reference to a reference. And then we have the move assignment operator, which returns a reference with an operator equals. We'll look at that again. And finally, again, the destructor, which is the tilde class name equals default. And again, the good news is you can use the default ones if there's nothing fancy you're doing with your class. And you don't even have to specify that you're using the default ones. You can, so this class definition is exactly equivalent to the one we had before, right? If everything you write is default, you may as well not write them at all. The compiler will be very, very happy about to interpret that in the same way. So, a fair word of warning. Say we have a class called X, which with a constructor which is just supposed to print out constructor of X. Now, usually I'd ask you here to take a guess what this might end up printing out. In this case, I'll just tell you. In fact, what happens is you get nothing. You get no printouts. Why? Well, this is what we call the most vexing parse, because this bit here, while you would like it very much to be instantiation of a type of a variable called lowercase x with no parameters of type capital X of our class, what this looks like to the compiler is the declaration of a function called x, which takes no parameters and returns something of type x. Right? So variable initialization and function declaration can be ambiguous, and that is, and in case of an ambiguity, the compiler is always going for function declaration. So be careful about that. It's actually quite easy to walk into that trap. Try and initialize your object in a different way. So skip the parentheses here maybe. Let's move on with some more typical member functions, which are getters and setters. They are not special member functions, but they're very typical and very commonly used. The idea being for getters, a getter is any public member function that allows a caller to get the value of a certain variable, while a setter is a public member function that allows a caller to set the value of a member variable. And the idea is, this is how you control the access to private member variables. So you hide away direct access from yourself and from other developers, and you force them to use specific getters and setters to access those variables. The advantage being, you provide it allows you to provide an exact documentation of how to use it, what this variable is supposed to mean. You can internally perform checks, so you don't have to just return the value, you can, or set the value. You can check that it makes sense. Like you don't want to set negative pressure or negative temperatures or something meaningless like that. So it gives you control to the access. However, another bit of advice: use that with care. If you overuse it, you can kind of break encapsulation, which is kind of not the point, or the opposite point of what we're trying to achieve with object-oriented programming. So be specific. Only the things you need, only the things you want users and other developers to access. Implement them only for those. So how can they look like? Well, here's our complex number example again, with the constructor, two methods which return something, and here we have two getters. The real method is just going to return the real value, and the imaginary emag method is just going to return the imaginary value, or internal private variable. Similarly, for the setters, all they do is set the values in this example. But again, you can do more. Nothing prohibits you to do more than just setting. Now, there's something else special going on, which is called the so-called the implicit object parameter. So, if some of you have done or written programs in Python with object-oriented programming, you may be aware of the self. If you write a member function in Python, it's going to be the first parameter. It always has to be self, which gives you access to the object itself. Similarly, C++ has a point, gives you access to that with a pointer called this. So the implicit object parameter is the object on which a function member is called. So if I instantiate and initialize one complex number and I want to use it or my object, if I want to use a member function to do something, then my object here, the one that is calling the function, is going to be the implicit object parameter. And this gives you access to to the member function to access the object it was called in. And this is again the this pointer, so literally THIS this. So its value is going to be the address of the implicit object parameter. And with this, you can access anything inside your object, including the object's address, right? So a typical use case would be if you need to return a pointer or a reference from a member function or access it, or where it also can help is to resolve a name ambiguity between local variables and member variables. If I have a local variable which looks exactly the same like a member variable, if you specify this, it's always going to be a member variable. Yeah? So here we are specifying that this is always going to be this classes A, so that this member variable A. Okay, now moving on a little to the concept of encapsulation more broadly. The idea is encapsulation refers to the grouping of data and methods which operate on this data, with the idea to protect the data from erroneous usage. So you want, in a program you always want to have a certain data of a state, whatever you need, and you want to perform operations on it. And the encapsulation is the idea, we're going to put those two together in a single capsule, and we're going to control access to it so that mistakes are prevented. Right? So we can enforce encapsulation in C++ using these class types, such as classes, unions, structs, to group data, so data and member functions. We can control access using access specifiers such as private, public, protected, and we can limit modifiability. So we can tell the compiler and ourselves what is allowed to be modified and what isn't. And I know we went through the const modifiers or qualifiers already in the procedural programming session, but let's do it again once more really quickly. So the const qualifier, it defines that the type is constant and defines that the initialized data object is immutable, so it cannot be changed. That's why it's constant, right? Therefore, the value of the object is set at initialization and cannot be changed anymore. However, in C++, you can also declare methods or member function as const. So if a class's member function is declared const, if it follows the function's parameter list, I'll show you an example in a minute. So it's after the parameter list, it specifies that this function will not modify the object. So essentially this function will only read this object's data at best, if at all, but I will not modify it. So if you try to modify a const qualified object, you will get a compilation error. That's kind of the point of it. And it helps to enforce encapsulation by stopping developers from trying to modify things they really shouldn't be modifying. That's the whole point. Declare it as something, this should not be touched. You can only read it, you cannot write into it. Right? And the good practice is spam const. Use it whenever it makes ever so little sense. Personally, I probably overuse it because it also tells me you're not intended to modify this at any place. And if I try to, it means that I haven't thought this through and I may need to reconsider what I'm doing. So both for member functions and their parameters, just add const. And so we can go through some examples here and see on the next slide what they actually mean. So here just the definition of an integer with the name a equals 5. So we give it a value. We can call this const, or we can put const after the int, or if we have a pointer here, we can declare a pointer const, or we cannot use it at all, or we can use it after the asterisk and before the name, or we can use it twice in here, before and after the asterisk for the pointer, or we can use it for a reference. So what do those things actually mean? What effect do they have? This means we have an integer with a value of 5 which cannot be changed anymore, so it's constant. Int const b does the same. Now const int asterisk e, so we have a pointer called e, which shows to the address of a, means e is a pointer to some integer, and that integer is constant. So what I'm telling the compiler here is, whatever this pointer points at, this thing over there, I will not modify. Yeah? This is just no const at all. Here, same again. Now we have a pointer to an integer, and then a const called g. And here it's different. Here I'm saying g, so the address I'm pointing to, this variable which holds the address, I'm not going to change that. Whatever I'm pointing to, that I may change. That is mutable yet. That is mutable still. I have not forbidden it from being immutable, but what the value of this pointer, so the address it holds, I will not change that. And now we can do both. So twice const, which means I will neither change the value this pointer holds, so the address it points to, nor will it modify whatever is in memory of that address. So nothing gets modified at any place. And here, finally we have a function which returns our value of type const reference to an integer. So that means we are getting a reference back to an object which will not be modified anymore. Now, in general, the const qualifier applies to the thing left of it. If there is nothing left of it, then it applies to the thing right of it. So bottom line, what you should be doing is reading types from right to left, not left to right. And yeah, fun fact, there is no such thing as const reference, because references are not really objects. And now, as I mentioned before, we have these const qualified member functions or member methods. And this is when we put so we had the getter functions called real and imaginary, or imag, which return the real and imaginary parts of the function. And if we put it after the parameter list, the const, this means this function will not modify whatever it is. This function will not modify the object. This is going to be a read-only function. Yeah? And this is the correct syntax here. It put it after the parameter list. Okay, now moving on to, or a little back to access specifiers. We had, we talked about public and private access specifier. Now, sometimes it can be helpful to let a few other classes still have access to private variables and members. Yeah, it can be helpful to still give them access. And you can do that by declaring this other class as a friend class. Right? So it appears in a class body, so we would say friend class, whatever the name of the other class is. And this gives that function or another class access to your private and protected members if there's a friend declaration appears. But friend functions are not member functions. Right. Another topic we should look at is so-called operator overloading. Now, you will be used from native types such as integers, doubles, floats, that you can apply operators to them, such as integer A plus integer B, right? So A plus B. You can apply the plus operator, minus, multiplications, divisions, module operators. You can use the increment operators, plus plus, and things like that. And to do that, we can also specify that for our own types, so for our own classes. And as a short recap, C++ allows function overloading. So you can define multiple functions with the same name and same return type. So they have the void return type, they all have the same name, but a different parameter types. That is permissible in C++. C does not let you do that. But we're working in C++ here because C doesn't have object-oriented programming and classes. So here we are allowed to do that. And we are also allowed to do that for operators in a very, very similar way. It just needs a bit of a different syntax, which may look a little weird, but it's quite easy to get used to. So operators are essentially special functions with special function names Yeah, they start with operator and then the operator that you're actually using, and they're defined as such by the C++ standard. So we have, for example, the arithmetic operators, plus, minus, multiplication, division, modulo, increment and decrement operators, like the plus, plus, and minus, minus. So if you have some integer a plus plus, it will increment a by 1. You have the so-called compound assignment operators, so like plus, minus, minus, plus equals, minus equals, things like that. So a plus equals 5 means a equals a plus 5. So increment a by 5. That works. You have logical operators such as comparisons, smaller to, smaller equals, greater than, things like that. And what we call operator overloading means to overload any of these, so same function name, different function arguments, any of these operators for our custom build type, so for our classes. And to do that, we have to look into a little bit more specifically. What we are working on here is what we call binary operators. And a binary operator is an operator which acts on two operands. So we have a left-hand side and a right-hand side, right? A plus B, A smaller than B, right? Two operands. So there are two options to overload binary operators. One is as a member function with a single argument, or as a freestanding, which may potentially need to be a friend function, which has two arguments. And I'll show you examples in just a second. And the good practice is that overloaded operators should always behave similarly to operators for built-in types. So if you define your smaller as operator to do what the equivalent of a built-in would do with a division, you're going to give yourself a hard time for no good reason. So maybe don't do that. And for commutative operations, such as, plus, multiplications, equals, the operator overloads are also expected to preserve that. So what does it look like in practice? So here, we're going back to our complex number class, and we want to define the operator plus. So we want to be able to add two complex numbers together. So here we're doing it outside of the class, so we need two arguments. Both of them are going to be constant, because what we're going to do here is return our result. So we're going to instantiate a new result. We're going to sum up the real parts, we're going to sum up the imaginary parts into the new object and return the new object. So both of those are going to be read-only. Both of the parameters are going to be read-only, that's why they're constant. And again, to overload the plus operator, this is what we need to do. You call the operator, so the function is with the keyword operator and the plus. That's how this will allow us to, in fact, use some complex number A plus complex number B, just as you would use integer A plus B. And here's the second option I mentioned, where we define it inside the class. Now, inside the class, you only need to define one extra argument, so whatever we're comparing it to, so the right-hand side, where we're doing the exact same thing, but this time we can access the member variables directly here, so we don't need the left-hand side. Yeah. Okay. Similarly, the copy assignment operator, so it's just what you probably assume as equal. So if you use integer a equals b, that's our copy assignment operator, right? Where we take an already initialized object. So this is not the copy constructor. This is the assignment operator. So we take an already initialized object and assign it a new value from an already existing object. So in general, this assignment operator should return by reference, while arithmetic operators should return by value. So here, for example, the example usage would be we have a complex number A initialized, we have a complex number B, and the copy assignment operator equals would be here. And same, what we're doing here is defining it outside, well, inside of the class, operator equals. So this is what we want to access, equals. Comparing it to other. And that's where we're going. Let's skip the question for now. We're running a bit low on time. There are, however, a few operators which you are not allowed to modify or overload, because you would frankly just break the language if you do, which are the dot operators, the namespace resolution operator, and the conditional operator. Because, yeah, it just doesn't make sense. So the language prohibits you from doing that, because you would just break way too many things which don't make sense. Yeah, here's a link with more info. Now, moving forward, it's time to look into the concept of composition, polymorphism, and inheritance. So, composition is the concept of building a new data type by combining existing data types. And the composition model it models a has a relationship, such as a book has a set of pages, or an STD vector has an iterator, so it has something in there. So specifically, the class types can consist of member variables which are other class types, which will kind of make sense if you start thinking about native types of C++, such as integers, floats, and doubles. They are all just classes too, just predefined ones which you don't have to do, right? So it's classes all the way down. And typically, you will use that when you want the features of an existing class, such as, I want to have an integer and I want to be able to do integer computations with it. Those are the features of the integer class, right? If you want those features in an existing class, you add it in there, but if you don't need its entire interface. If we need to replicate the entire interface, that's what we have inheritance for, which we'll talk in a minute. Okay. A different concept, which helps with an encapsulation and object-oriented programming, is polymorphism. And we differentiate between three types here. What we call ad hoc polymorphism would be if we write multiple implementations of a single function, one for each type you want to support. So, for example, stupid functions say add +1, right? So then I write one for integers, then I run one for floats, then I write one for doubles, etc., etc. And that's when we get into function and operator overloading. Write a function which does the same, but for different data types. Now, another type of polymorphism we call subtype polymorphism, which is where we are relating data by some form of substitutability. So we can, in cases where we can just substitute data types. So the idea would be to write a function, for example, with a supertype instance, and then we make derived types of that which retain the supertype's properties, let's say, but may or may not add more stuff to it. For example, if you're going back to our example of you writing a library which gets you a window, so like a window on your screen, a computer window where your program is running, right? Something you would like to write would, for example, be class button, right? because all buttons are going to be, for example, clickable. So you don't want to write that 10,000 times for every different type of button. What you're probably going to do is write what we call a superclass called button, and it will have a property called clickable, and it will probably have a property do something when clicked, something like that. And then for every different type of button, be it on your menu or to close the window or whatever your program does, maybe you're writing a video game and you click on the menu items, or you click on whatever, they can then inherit those properties. Button has a name, or it's clickable and it does something when it's clicked. But you may want to specify, the shape of a button, or where it's, or its color, etc., and what exactly it does. You will want to specify that on a case by case. So this is when we are using inheritance. Right? And the final type we're looking at today, or talking about today briefly, is called parametric polymorphism. When I'm writing implementation of a function, which would apply generically and identically to values of any type. Okay, now with the thing I already veered into inheritance, let's look more into it. The idea being, it's the concept of building new data types by deriving from existing data types, right? So inheritance models is a relationship. So maybe in a more real-world example or less digital example, we could have a class, let's say, called vehicle. And all vehicles will have some property or a method which will be called a drive. But it will look differently for different objects, right? So then I may be more specific and say, okay, but now I want a car. I want a class of type car, right? That describes the type car. And ideally, a class is a vehicle, so it will inherit properties from the vehicle class. Similarly, the bicycle class will inherit from the vehicle class. So you repurpose certain parts of your program or of an object, and you just pass it down the line because you intend that whatever inherits those properties, so member variables and member methods, will use them again and will need them again, right? So typically, you want to use and reuse the interface from existing classes inside a new class, but maybe not all of its implementation. Maybe you want to replace some, or maybe you want to add more to the implementation, which, the more specific you get, the less general you are by definition. Right? So derived classes can be more specific. That's kind of the point. So here's how it looks like. Commonly we're speaking of based and derived classes. So let's say we have a base class, which we have a constructor which just print out, hey, we're constructing something, and we'll give it a function called function1, which will be called, which just print out function1, right? And now we're defining a second class, which we call derived, and we give it public access to base. So essentially, say anything which was public in base will remain public, right? Inside. So this is the inheritance access modifier. So we are inheriting from the base class, and we are writing a constructor, and the constructor will just print out, hey, I call the constructor of the derived class. So what's the entire point of this? Well, let's look at a small example. Let's call it, let's instantiate an object base of type base and an object of type derived. And now we're gonna, excuse me, we're going to derive, we are going to call function 1 on B, and we're going to call function 1 on D. And already you can see an advantage of inheritance, because if you look back, so we're calling B is of type base and D is of type derived. Now, if you look back, we defined a function called function 1 on type base, but we did not define it for the class derived. The big advantage here is, because we're inheriting from base, derived also has a function 1. So what's the output here going to be? Well, first we're going to call a constructor of B, and then we're going to call a constructor of D, but in fact, because it's a derived class, it will first call the constructor of the base class for D, and then the constructor of the derived class for D. So this is why you get two outputs here. And then B is going to print out function 1, and then D is going to print out function 1. Yeah? So this code works. D inherited the method function 1 from the base class. All right? Now, we get here, as I very briefly touched upon, we get another access specifier. You see, we specified here that the way we inherit from the class base is public. So here, just as inside the class, it specifies the access rules for members until the end of the class or until another access specifier is encountered. And here we get something which is we haven't talked about, but which now starts to become important. So we've seen private access specifiers and public ones, but in fact you also have protected. And a member function or variable, a protected one, can only be accessed, so it's essentially private, unless the thing trying to access it is either yourself or a friend class or a derived class. So yeah, nothing on the outside, but deriving classes or classes which inherit from this class will be able to access members with the protected access specifier. Right, so we're nearing towards the end. Bear with me for a bit. Something else we should talk about is, runtime polymorphism, where we're overriding some of the base class functions in a derived class. So the idea is what we call virtual functions. So maybe your base class wants or defines a property or a method, a member method, which makes sense for the base class, and you need some contents for it, but your derived class needs a different specification. Right? If we go back to, let's say, a vehicle which has a function called drive, and let's say you essentially write something along, it goes on 4 wheels, or all 4 wheels start rolling, then if your car class inherits that from the vehicle, that makes perfect sense. If your carriage does it, it also makes sense. If your all-terrain buggy does it, it also makes sense, right? That still works. When it stops making sense is, for example, for your bicycle class, because you don't have 4 wheels, right? So in this case, you may want to overwrite that. And this is what we call virtual functions. So you can tell the base class, look, this function is virtual, which means base derived classes are allowed to overwrite that, right? So what we can do here, back to our example, we're going to overwrite function 1 here in the derived class, and it'll say we're calling it in derived instead. But here in the base class, we're also going to say we call function 1 in the base class, but we need to declare it virtual. Otherwise, the compiler is going to be mad at you. Right? Now, we can go even further and say, well, look, we can declare a function virtual, but we can even further make it abstract. And just by adding equals 0. So here's the example. If we have virtual void function equals function 1, and here you would specify your entire function, even in parameters you had, you would put them in here, equals 0. What it tells the compiler is, look, this is an abstract function. So the base class basically defines the interface here. So this is what the function is supposed to look like, but I'm not delivering an implementation of it. And any class which inherits from me, so which is derived from this, must implement this function 1 or whatever you need yourself. And the idea being, you specify well, the name and the prototype once, and this will ensure that anything you derive must have one of those in there, which means you can call it on any subtype of this object. You will be able to call one of these functions, or the compiler will not let you instantiate the class as long as it's abstract, right? So you will force subclasses or derived classes to implement them. Now, what is also possible, and what people do, and which is a sensible thing to do in certain applications, is to define classes which solely consist of abstract operations, which is an interface, right? Now, you are not limited to inheriting from only a single class. It doesn't need to stop at one. You can inherit from as many classes as you like and as you need. Yeah? So here, for example, we have 3 different classes, A, B, and C, and D can inherit from all 3 of them. That is, in principle, not a problem. In practice, you can get in very, very big trouble if A, B, and C have, for example, a common superclass and start overwriting things themselves. So if, let's say, for example, A is the superclass of both B and C, and B overrides function 1, and C overrides function 1 in a different way, and D, then you end up with a diamond shape. Then what's D supposed to inherit from? Right? The function for override from B or C. So that can be a problem. So do try to avoid that. It will spare you a lot of headaches. Just try and restructure your code in a slightly different way, right? But yes, you can inherit in principle from as many classes as you like. And yeah, so one of the final slides, the Liskov substitution principle, named after Barbara Liskov, is the idea that object of some superclass should always be replaceable with objects of its subclasses without breaking the application. And in fact, to a certain degree, object-oriented programming and inheritance is the entire point of that. So that's the entire point of it. I can specify certain things just for a superclass, and it will be applicable to all my subclasses, right? Now that is a good guide, but only works in the case of public inheritance. So if you really inherit all of it, with an easy relationship, and it will not be, obviously not be applicable to interfaces, because interfaces cannot be instantiated. right? Therefore, you cannot run a superclass in there because right. Okay, and we made it. To sum things up about inheritance, it represents is our relationship. Like the sun is a celestial body, the car is a vehicle, and so is a bicycle. So a bicycle is also a vehicle, right? So the whole idea of it is it enables us to model the real world more accurately, and it makes things easier for us. It avoids to have to write code duplication because you can literally just reuse the same thing without typing it up again. And it also means that we can write, it allows us to write functions for a whole set of different class types, which then again get inherited, right? So it gets us a chance to save a lot of work, save a lot of trouble, save a lot of headaches of what applies where. Right? And that was it for today's session.